Hi everybody. In this session I'm going to talk about Postgres sharding. I will cover this agenda starting by a few words about me, what is database sharding, how it is implemented in Postgres, a quick tour of some of the key features, and a few words about the missing pieces, and the conclusion. About me. So my name is Julien Tachoires. I'm based in France, in the beautiful city of Bordeaux. I'm a PostgreSQL fanatic since 2009. I've been a database administrator, a database consultant, open source developer, and CTO. And today I am working as a PostgreSQL performance engineer at EDB. So let's start with database sharding definition. So what is database sharding? It's basically the idea of distributing data across multiple database instances, called shard. Each database instance is hosted by a dedicated machine or server. Database sharding should be considered as an option when database size or IOPS or CPU usage exceed what a single server can deliver. Database sharding technique is known as horizontal scalability, meaning that scaling up the database consists in adding more servers, while vertical scalability consists in using more powerful resources on a single machine. Distributing data across multiple database instances follows a strategy. This strategy is composed by a method, which is basically an algorithm, and a shard key. This strategy can be viewed as a way to group rows together with the same criteria on the same node. So based on this strategy, the database cluster will be able to know exactly where each row is located. The part of the database cluster in charge of routing data between clients and the shard nodes is the coordinator node. This coordinator node acts as a database proxy between clients and the database nodes storing data. So for taking full advantages of sharding, the client should use the shard key when it is executing queries on the coordinator node. For example, on the diagram presented here, the sharding key has been defined as user ID, and this way the coordinator node knows, for example, that the user ID 4 is located on shard 1, and it doesn't have to scan the other shards to find it. But what happens if we use, for example, the first name column as the shard key and execute the same query? In this case, the coordinator node does not know where the data is located because the shard key is not used, so it has to scan all the shards. And depending on the query executed, part of or the whole query is pushed down from the coordinator node to the shard node. Several data distribution methods exist in sharding world, leading to some well-known strategies. And the list-based method defines explicitly which shard key value appears in each shard. This method will be used by a geographic sharding strategy. In geographic sharding, the objective is to keep user data as close as possible to their geographical location. Range-based distribution involves dividing data into continuous ranges determined by the shard key value. This method is particularly useful to group time series data by a period of time. And the hash-based sharding uses the result of a consistent hash function applied to the shard key value to distribute rows across the cluster. This method is useful to split data by entity. So let's take, for example, an application in charge of storing user data like contacts or documents. With this approach, all user-specific data will be held by the same shard node, making joins operation, aggregate operation, and foreign keys definition easier. Now let's take a look at Postgres built-in implementation of sharding. The Postgres foreign data wrapper extension is a very important piece of the built-in sharding implementation. This extension has been added in version 9.3, and it allows access to data stored in a remote Postgres server. So basically, from a local session, we can access remote data through regular SQL queries. To use Postgres foreign data wrapper capabilities, 3 different database objects must be defined. The first one is the server, which defines remote instance characteristics like the address, the listening port number, and the database name, for example. User mapping is used to make the relationship between the user connected through the local session and the user that will be used to connect to the remote database server. And finally, the foreign table object is a pseudo table, not a real table, which is linked to the remote table. So using the Postgres foreign data wrapper is not complicated. First of all, we have to create the extension on the database. We want to make it available. And then we can create our server object with the create server statement. And at this step, we have to define the target host address, the listening port, and the database name. And once our server object is created, we can now proceed with user mapping creation with the help of the create user mapping statement. At this step, we can define the username and password that will be used to connect to the remote host. And each user mapping is attached to a Postgres foreign data wrapper server. And finally, we can proceed with the creation of our foreign table with the help of the create foreign table statement. And like user mapping, each foreign table is attached to a foreign data wrapper server. So the other major piece involved in the built-in implementation of sharding is table partitioning. Table partitioning provides data distribution across multiple tables. Until version 10, table partitioning was based on table inheritance principle, meaning that we have one parent table and n child tables inheriting from parent table definition. So with this approach, we had to create some rules and trigger functions in charge of applying data routing. So it works, but definitely not optimized and not easy to work with. But since Postgres version 10, a declarative approach is available and makes things easier and better. With declarative table partitioning, the partitioned table is a kind of virtual table without any storage, meaning that no data can be stored on the partition table. Data distribution across the partitions relies on a partitioning key, and Postgres supports 3 different partitioning forms: list partitioning, range partitioning, and hash partitioning. Now let's take a look at some different data distribution strategies that can be applied with the help of Postgres declarative partitioning. If we take the geographic distribution case, setting up this strategy consists in having a column that will be used to store the region code, and for each region we have a dedicated partition. So with the help of list partitioning and based on the region code, data will be located into the partition related to that region. One interesting recent feature is that it's now possible to define a default partition. About time series, with Postgres declarative partitioning, we can create, for example, 1 partition for each month, and then, based on a time frame, time series data are grouped by months, for example. And finally, Postgres hash partitioning form allow us to distribute data by entity or entity group. So in this case, the partitioning key value is hashed, then a modulo operation is calculated based on the hash value and the number of partitions. So if the remainder is 0, then the data will be located on partition 1. If the remainder is 1, then the data will be located on partition 2, and so on. Declarative table partitioning and Postgres foreign data wrapper are the key features on which built-in sharding relies. In Postgres built-in sharding, usual table partitions are replaced by foreign table. So in this case, the foreign tables are created as partitions of the partitioned table. The partition table is located on the coordinator node. Remote tables linked to foreign tables are located on the shard nodes. One Postgres foreign data wrapper server must be created per shard node, and one user mapping must be created per server. So before going further, let me show you the database model used to highlight some of the key features of built-in sharding. So to highlight some of the key features, we are going to use a pretty simple architecture composed by 1 coordinator node, 3 shard nodes, 2 partition tables. So the goal here is to implement a lightweight document storage application. The shard key is user ID, and we are going to use hash partitioning form. Databases have been populated with 5,000 users and 25 million of documents. So let's move on improvement and key features. Aggregate pushdown. So the Postgres foreign data wrapper aggregate pushdown feature was added in Postgres version 10. It consists in executing aggregate operations on the remote server instead of fetching data and executing the aggregate operation on the local node. Aggregate pushdown does not provide direct benefits for sharding, but this feature will be used by other more advanced techniques. In general, delegating operations to remote servers helps to save resources on the coordinator node, and it helps to reduce network overhead, and at the end, it improves global scalability of the system. Another important feature added in the version 11 is the capability to write data into a foreign partition through a partitioned table. It means that the insert, update, or copy queries that are issued on the partition table are routed to the right shard node. Of course, this capability is more than an important feature. It's a necessary feature for built-in sharding. About partition-wise join. The goal of partition-wise join is to break down a join between partition tables into joins between their partitions. This was added in version 11, and partition-wise join is disabled by default because it can use significantly more CPU time and memory during planning. So to enable this feature, the enable partition-wise join parameter must be set to on. But what are the benefits for sharding? So, well, instead of executing the join operations on the coordinator node, involving the need to transit data through the network, join operations are executed on the shard nodes. So let's take a look at the following example. So in this case, we want to list all the documents attached to users with a first name equal to Tony by executing the following query on the coordinator database. So if we take a look at the execution plan, we can see that foreign scans of users partition are issued and 6 rows are fetched because of the where clause. So we are basically scanning all the users partition, and only 6 rows are fetched. And then foreign scans on documents partition are executed, but this time 25 millions of rows are fetched. 25 millions is the total number of documents in our database. And at the end, the join operation is executed on 6 users on one side and 25 millions of documents of the other side. And the total execution time is 47 seconds. Now, let's execute the same query, but this time with enable partition-wise join set to on. So this time we can see that the execution plan is more simpler. We have only 3 foreign scans executed. And for each foreign scan, the join operation is pushed down to the remote server and applied at the partition level. So execution time improvement is huge in this case because from 47 seconds to 123 milliseconds. So this is very huge. Another interesting feature, still in the same fashion, is the partition-wise aggregate. So the principle here is the same as with partition-wise join, meaning that instead of applying aggregate operations at the partition table level, the aggregate operation is executed at partition level only. Making it happen requires that the key used by the aggregate operation must match the partition key. For example, if you group by a column that is not the partitioning key, partition-wise aggregate cannot be used. So like for partition-wise join, partition-wise aggregate is disabled by default because of CPU and memory usage at planning time in case of a very large number of partitions. And to enable it, the enable partition-wise aggregate parameter should be set to on. And like for partition-wise join, the objective when using it in sharding is to delegate aggregate execution to the shard nodes. So, another example. So this time we have to do some kind of reporting and we want to export for each user ID the number of documents, the average size of each document, the minimum size and the maximum size. So let's execute this query on the coordinator node. If we take a look at the execution plan, we can see that we have 3 foreign scans issued, basically 1 per document partitions, and 25 million of rows are retrieved by the coordinator node, and the aggregate operations are executed by the coordinator node, and almost 5,000 rows are returned by the query, which is the number of users in our database. And the execution time is 49 seconds. Now, let's execute the same query, but this time with enable partition-wise aggregate set to on. So this time, we can see that the aggregate operations are pushed down to the shard nodes, and only 5,000 of rows are transiting between the shard nodes and the coordinator node. So once again, the execution time improvement is huge. It falls from 49 seconds to almost 2 seconds. Another interesting feature added recently is async append. Async append allows foreign scan parallelism, meaning that instead of scanning each foreign table sequentially, they are scanned in parallel. More asynchronous operation will be supported in the future, and to enable asynchronous append, Postgres foreign data wrapper servers must be configured for using it by setting the async capable option to true. So it can also be enabled at the foreign table level by configuring the same option to true. And the enable async append parameter controls the usage of async append at the planner level. So to illustrate asynchronous append capabilities, let's consider the following query. So this time we want to know how many JPEG files or JPEG documents are present in our database. So if we take a look at the execution plan, we can see that 3 foreign scans are issued on the documents partitions, and the execution time is 5.5 seconds. Now, let's do the same thing, but with the async capable parameter set to true. So in this case, we can see that instead of having just foreign scan, we can see that some async foreign scan issued, meaning that each scan is executed in parallel at the shard level. So the execution time is twice as fast as without async append, so this is a big win. But we should keep in mind that there is no parallel mechanism involved on the coordinator side, just asynchronous execution. But making things asynchronous leads to parallel executions on shards. And the last key feature I wanted to highlight is the bulk insert. So this feature was added in Postgres 14, and the goal of this feature is to group insertion of individual rows in a batch. It works at Postgres foreign data wrapper level. So what does that mean? When many insertions are coming, instead of sending them one by one to the remote server, they are sent in a batch. For the moment, only the insert statement is supported. And by default, bulk insert is not enabled, so you have to configure it through the batch size option at server or table level. So, to highlight the benefits in terms of performance, let's measure the execution time of the following query that is going to insert 1 million of rows into the user's table via the coordinator node. So without bulk insert, execution time is 466 seconds. When we set the batch size to 10, we can see that the execution time is now 54 seconds. And when we set the batch size to 100, the execution time is 7.3 seconds. And with the batch size set to 1000, execution time is 5.5 seconds. So when using built-in sharding, if you plan to insert a massive load of data, don't forget to tune batch size because it could help.
When you did this test,
yeah.
you're selecting the same name, so it's going to go to the same shard, the same partition. Did you do it where it has to find out which partition it's going to go into?
Yes, yes. Actually, on the users table, we have, let me go, we have the user ID. This is a big int, but a big serial. So we have a sequence attached, and each new user ID generated will make the insertion of this user into a different shard. So about the missing pieces of built-in sharding. Partial aggregate pushdown is the capability of executing partial aggregate operations at the shard level, and then proceed with the final aggregation based on partial results at the coordinator level. So in general, partial aggregate pushdown is required when the aggregate operation involves data located on multiple partitions. So far, multiple patches with different approaches have been submitted, and this is still work in progress. So one more example. Let's consider we want to count the total number of documents we have in our database. So we are going to execute this select count star query on the coordinator database. So if we take a look at the execution plan, what's going on here? So once again, the 25 millions of rows coming from the documents partitions are fetched and the aggregate operation is executed by the coordinator. And the execution time is, once again, 49 seconds. If we want to simulate how the partial aggregate pushdown may work, let's rewrite this query this way. We are going to count the number of lines of each partition, and then we are going to do the final sum once we have each count. And so this is a very dirty query, but this is just for illustrating how partial aggregate pushdown may work. And so if we take a look at the execution plan, this time we can see that the aggregate operations are pushed down because we are working at the partition level. On the execution time, we can see that we fall from 49 seconds to 1.7 seconds. So this is again a huge win. A few other areas for improvement can be made. For example, there is no tool available for helping in shard management. For example, when using hash partitioning, if you want to add new shard nodes to the cluster, it will imply rebalancing some of the rows because the total number of shard nodes is different, and the distribution strategy based on the modulus calculation will provide different results. So you have to move some record from one partition to another partition. In terms of high availability, there is no built-in mechanism helping here. So for each shard node, we should set up at least one standby node and its own high availability mechanism. Another solution would be to implement data redundancy across shards through logical replication, but it implies additional tooling. And about distributed transaction, atomic commit and visibility involving multiple Postgres servers are missing. So in conclusion, the built-in sharding approach based on declarative partitioning and the Postgres foreign data wrapper extension is gold because it relies on existing infrastructures, meaning that sharding will take benefits from future improvements made on them. We can say that since version 11, Postgres provides sharding capabilities. So yes, not all use cases are supported yet, but some of them can be implemented. And you can find here some references that have been used by me to work on this presentation. And that's it. Is there a question? No? So we are good. Thank you.